Salam, peace be upon you. My name is Muhammad Laik Sabiqi, the father of holophase. We begin with a stitched achievement report, so we do not lose the thread. So far, in episode 14, we have built a strict compiler for public structure. We start from phase comparisons only, not absolute phase. We license finite windows with passports, coherence thresholds, identifiability checks, and a maximum derivative ceiling. We lift phase locally only to differentiate. We cut and excise only to stay honest. And we certify a clean domain where operators are legal. We extract the first public object A, meaning the derivative of the lifted phase, and then finite jets up to the allowed order. We collapse all meaning to what survives gate shifts, chart changes, cut moves, and window refinement. We built atlases of overlapping windows, enforced lawful translations, and demanded triple overlap closure so global claims can exist at all. Now we enter block G, where we allow something that can feel almost magical at first, but is actually one of the cleanest ideas in all of science. A loop can remember. Not in the emotional sense, not in the story sense. In the strict public sense, a loop can carry an integer-like memory token, a certified stamp, even when every local point looks normal. This is part 28. Holonomy as a global memory token, and we will speak it in everyday language, but we will not cheat the rigor. Here is the mission, spoken plainly. We will define certified loop memory tokens built only from A, along loops that are fully inside a certified domain. Then we will enforce the key rule. The loop's memory is public only if it does not change when we gently reshape the loop inside clean territory. If it changes under allowed reshaping, it is not a real memory token. It is counterfeit. It gets revoked. That is the whole part, and we will make it feel obvious. Let us start with a picture you can hold. Imagine a city at night. You are walking with a small lantern. The lantern lights only a tiny circle around your feet. You cannot see the whole city. You only see local details. The next step, the next corner, the next wall. That lantern is like our licensed window. It is local. It is finite. It has a passport. It is honest. Now imagine you take a walk that starts at your hotel, goes around some streets, and ends back at the same hotel. You have walked a loop. Here is the question. Can that loop tell you something that no single step could tell you? Yes, because loops can detect what is inside them, even if you never step inside it. If you walk around the fenced construction site, you can return to your hotel and still know, with certainty, there is a blocked region inside my path. You did not enter it. You did not measure it directly. But the loop tells you something global. There is a hole in the accessible territory. That is the first deep lesson. Loops do not only talk about points. Loops talk about the shape of what is allowed. Now we translate that into our holophase language. Our primitive is phi, a cyclic comparability. We do not speak absolute phi. We only speak differences of phi inside licensed windows. To do calculus, we take a local lift of phi. Lift means we temporarily unwrap the circle into a line so we can take derivatives. We call the lifted phase phi tilde. Then we define A as the derivative of phi tilde. Say it out loud like this. A equals d phi tilde. A is the first public object because if we shift the lift by a constant, the derivative does not change. So A does not depend on arbitrary lift choices. It survives translation. It is public. Now the loop memory is built only from A. We take a loop, gamma. Gamma is just a closed path. Then we compute the holonomy by integrating A along the loop. Spoken slowly. Holonomy of gamma equals the integral around the loop gamma of A dot dl. In words, We walk around the loop and we add up the tiny phase changes that A says we accumulate along each small step. That sum is the loop's memory. Now we make the strict point that separates real memory from fake memory. If you take the same loop and gently reshape it, staying entirely inside the certified domain, not crossing any excised zones and not crossing any defects, then a real memory token must not change. Because if the memory changes just because you drew the loop a little differently, then the memory is not about the territory. It is about your pen. It is about your drawing style. It is bookkeeping noise. So the rule is simple, and it will become a law for the whole framework. A loop's memory is public only if it is invariant under admissible deformation inside the certified domain. In everyday language, if a loop is a witness, it must tell the same story no matter how you gently reposition the witness. As long as the witness stays in clean territory and still surrounds the same inside. Now let us make this feel real using 3 everyday analogies from 3 scales: a room, a city, and a planet. First, the room. Imagine you are in a house and the floor has one hidden trapdoor. You do not know where it is. The room looks ordinary everywhere you can see. The floorboards look the same. You walk around and everything feels normal. Now, you take a rope and you lay it on the floor in a closed loop. You can draw a circle with the rope. Then, you gently slide the rope around while keeping it a loop, never lifting it off the floor. If the rope never crosses the trapdoor, then any memory we compute from walking along the rope should remain stable. It is the same ordinary floor. But if the rope encloses the trapdoor, something changes in principle. The loop class is different. You cannot shrink the loop down to a point without crossing the trapdoor. The trapdoor acts like a hole in the domain of safe floor. So now the loop tells you a global fact. There is an obstruction inside. Second, the city. Imagine a city with a roundabout that has a statue in the middle. You can walk around the roundabout. Now imagine 2 different loops. One loop goes around the statue once. Another loop goes around the statue twice. Locally, every step looks the same. It is just walking on pavement. But globally, the loops are different. They belong to different loop classes. One wraps once, one wraps twice. If our loop memory token is real, it should distinguish those classes. It should not care about the exact shape of your walk, but it should care about how many times you wrapped around the center. Third, the planet. Imagine Earth with the North Pole. Suppose you walk a loop around the pole. Any loop that encircles the pole cannot be smoothly shrunk down to a point without crossing the pole region. There is a topological difference between loops that encircle the pole and loops that do not. This is not about time or evolution. It is about the shape of the domain. Now we return to our holophase meaning. Holonomy is a token because it can be an integer-like memory that does not depend on local details. This is the crucial phrase that many people struggle with until they feel it. Loops can store global information even when local derivatives look ordinary. A can look smooth everywhere you sample. Jets can be normal everywhere. But holonomy can still be non-trivial if the domain has holes or defects or excluded regions. This is exactly what makes holonomy powerful. It is a memory of global structure, not local texture. Now we install the triunity reminder, because it must never disappear. Everything we do is still one differentiation, with 3 readouts. Omega is cadence, the rate of phase change readout. Kappa is texture, the pattern readout. Nu is drift, the transport readout. A loop memory token can be expressed in these readouts too, but we are not allowed to smuggle time, space, or motion as primitives. We only say, holonomy is a certified token computed from A, and any triunity interpretation is a later readout layer. In episode 14, we certified the structure only. Now we go to the gates, but we will speak them as a story, not as a checklist. Still, each gate will be unmistakable. First gate, loop certification. Before we trust the loop's memory, we must certify the loop itself. We must say, this loop gamma lies entirely inside the certified domain D. That means it does not pass through excised zones, it does not pass through regions where our operators are illegal, and A is defined along it. In everyday language, we do not accept testimony from a witness who kept stepping outside the courtroom. So, we issue a loop certificate. Gamma is inside D. A is defined along gamma. The loop is closed. The passport lineage for the data used to compute A is attached. Second gate, invariance. We must ensure that the loop memory does not depend on bookkeeping choices. If we shift the absolute phase by a constant, phi to phi plus constant, holonomy must not change. Because A is a derivative, and derivatives kill constants. If we pick a different local lift, holonomy must still be well defined, because again, we only integrate A, and A is lift invariant when properly certified. In everyday language, if the loop memory changes because we changed our naming convention, it is not memory. It is a naming artifact. So we stress test. Phi to phi plus constant must leave the holonomy unchanged. Lift shifts must leave it unchanged. Chart changes must leave it unchanged. Cut relocation must not change the value as long as the cut is bookkeeping and we account for it lawfully. Third gate, and this is the heart of part 28, deformation legality. We must define what gently reshape the loop means. It means we are allowed to deform gamma continuously to a new loop gamma prime, staying entirely within D and not crossing any defect or excised region. If we are in a defect-free certified region, then holonomy must be invariant under such deformation. This is the rubber band rule. If the territory is clean and there is no obstruction inside, we should be able to slide the rubber band loop around and shrink it down. And as we shrink it, any real loop memory should collapse to the trivial memory. So in a defect-free region, holonomy should depend only on the loop class. And if the region truly has no holes and no defects, the only class is trivial, so holonomy should be trivial. Now we state the prediction, but we keep it in episode 14 form. Not a future event, but a forbidden-ness footprint. Here is the prediction of part 28. In defect-free certified domains, holonomy depends on the loop class, not how you draw the loop. Meaning, if two loops can be gently deformed into each other inside D, then they must carry the same holonomy token. If we ever see a claimed holonomy token that changes when we gently reshape the loop inside clean territory, then something has gone wrong. Either the region was not defect-free, or the loop was not fully inside D, or A was not properly certified. Or we have aliasing contamination. Or we crossed an excision without admitting it. Or our computation smuggled geometry or lift dependence. So the prediction is also a discipline. Most mysterious loop effects vanish once we enforce domain legality and deformation invariance. Any residue becomes typed, either bookkeeping error or a real obstruction that must be cataloged as a defect token. Now the falsifier. Here is the falsifier, spoken plainly. Holonomy changes under an admissible deformation entirely inside a certified domain in a region verified defect-free. That is catastrophic. It would mean that loop memory is path-dependent, even when it should not be. It would mean our A is not behaving like a true derivative object. It would mean the compiler's meaning for loops is broken. In everyday language, it would mean two people can walk two gently different versions of the same loop in the same clean park, and the park would remember two different totals, even though there is no sinkhole, no elevator, no trapdoor, no hole. That would mean the park is inconsistent. So if that happens, we either withdraw the claim of defect-free, or we withdraw the certification of the domain, or we declare an escape candidate, a public structure that cannot be encoded by our holonomy token rule. Now let us bring the strongest part of the more technical version, but we will keep it gentle. We will not drown the listener in devices. We will use one simple physical image that almost everyone has felt: a closed electrical loop. Imagine a simple circuit, a battery and a loop of wire. The battery pushes charges. Now, if you go around the loop and you add up the voltage changes, you come back to where you started. So the total around the closed loop is zero, if nothing inside the loop is changing in a special way. That sum around the loop is a cousin of holonomy. Now imagine there is a changing magnetic field passing through the loop. Then something interesting happens. Even if the wire looks ordinary everywhere locally, the loop can remember the flux through it. The memory is not about a point. It is about what is enclosed. This is why loops matter in real science. Loops can detect enclosed structure without touching it. We do not need to say more than that here, because episode 14 is structure only. The only moral we take is, holonomy is a global memory token that can certify something about what is enclosed, even when local readings are ordinary. Now we give a cross-case story that anchors this to human life without reducing rigor. Think about a rumor moving through a village. Person A hears something and tells person B. Person B tells person C. Person C tells person A. Now we ask a loop question. When the rumor returns to A, is it the same rumor? If it is the same, the loop closes. The story is consistent. If it is not the same, then the loop picked up a twist. That twist is like holonomy. It is the net change after going around. Now, in healthy communication, if everyone is careful and honest, the rumor should not gain a twist. Any twist is a sign. Either someone made an error, or there is a hidden obstruction, like a misunderstanding or a missing shared definition. We are not claiming sociology is physics. We are using it as an analogy for the same structural principle. Loops expose global consistency and global memory. Now we speak the always true pipeline line, somewhere in the flow, because episode 14 requires it. We will speak it as one breath, like a mantra. License window, then passport and coherence and identifiability, then maximum derivative ceiling and uncertainty, then local lift, then cuts if needed, then excisions, then certified domain D, then A equals D phi tilde, then finite jets up to the ceiling, then invariance collapse, then topology and defects, then invariant basis, then stability and entities, then scale stratification, then escape test, then handoff. Now we return to part 28 and make the token explicit. Holonomy is not a vague feeling. It is not the loop experienced a lot. It is a number-like token computed from A around the loop. And because our phase is cyclic, the holonomy often lands in integer-like classes. It can count how many full turns the phase wins around something. It can count a defect charge. It can encode a global obstruction. In audio language, you can say it like this: we walk the loop. We add up the tiny phase changes along the way. If, after returning, the phase has effectively wound around the circle an integer number of times, that integer is the loop's memory. This is why block G is called integers and obstructions without particles, forces, or dynamics. We are learning how integers appear in nature without inventing little beads called particles and pushing them with forces. Integers appear because loops can wind. And winding is not a story, it is a topological fact. Now we perform the mandatory stress tests for part 28 explicitly, so there is no ambiguity. Stress test 1. Shift phi by a constant. Holonomy must remain the same. Stress test 2. Shift the lift by adding 2 pi times an integer plus a constant. A remains the same, so holonomy remains the same. Stress test 3. Change charts in an overlap. Since holonomy is computed from A, and A is overlap invariant when translations are lawful, the holonomy token must match across windows on overlaps. Stress test 4. Move the cut. If the cut is bookkeeping and we do not cross a defect, moving the cut must not change the holonomy token. If it does, then the cut was not bookkeeping, it was masking an obstruction, or we violated domain legality. Stress test 5. Refine the window. If the region is defect-free, the holonomy token should remain stable under refinement. Only the uncertainty should change. Now we write the audit artifact, but we will keep it narratable. The audit artifact of part 28 is a loop registry and holonomy log. It records which certified domain D we used, which loop gamma we certified with its passport and boundary description, the computed holonomy token value with uncertainty, a list of deformation tests we performed, meaning how we gently reshape the loop, and the before and after holonomy values. A failure localization report if anything changes, stating whether the likely cause is aliasing, domain violation, cut mishandling, or an untyped defect. In everyday language, we keep a notebook that says, this loop in this clean territory remembers this number, and it kept remembering the same number even when we reshaped it in all allowed ways. That notebook is the only reason holonomy becomes public. Now the revocation clause, because we always end with the knife that kills drift. If a claimed loop token is not invariant under admissible deformation inside the certified domain, it is rejected as non-public. It is revoked. It cannot be promoted into global structure. It goes to the negative archive with the failure classification attached. And we also add the companion warning, because this part is famous for tricking people. If someone claims a loop remembers something, but the memory changes when you redraw the loop slightly, then they are not discovering deep topology. They are discovering the sensitivity of their method. They are reading their own pen strokes. We do not certify pen strokes. We certify only what survives allowed redescription. Now we close the part with the carry, the one sentence that the listener should feel in their bones. Loops carry memory, but only the memory that survives gentle reshaping inside clean territory is real. Everything else is local noise or bookkeeping leakage. And we remind the listener where to go if they want the formal backbone. If you want to go deeper into the formal work behind this, including the exact definitions, the domain typing, and the proofs behind loop invariance and defect typing, you can find it on Zenodo by searching for holophase. Now we end in the correct episode 14 way. Structure certified, nothing happened. We did not tell a story about the universe evolving. We did not invoke forces. We did not add observers. We did not add meaning or value. We did not add probability. We did one strict thing. We added a new kind of certified word to our language. Not a point word, not a jet word, a loop word. A global memory token built only from A on certified loops. Public only when deformation invariant. Part 28 complete. Always, peace be upon you.